So we want to know how much confidence we should have in the estimated regression coefficient beta hat that we've estimated using ordinary least squares. We also have estimated alpha hat. We're not going to focus on the alpha hat, the intercept, very much. Instead concentrate on the estimate of the slope, how much the change in the x variable affects y, the outcome variable. So we've estimated this beta hat, but we know that a different sample would have enabled us to compute a different beta hat. And subsamples of our data could have been used, and they would have generated different beta hat. So you can imagine that we have lots of different samples from the population. We'd end up calculating lots of beta hats, and that would give us then a distribution, a probability distribution. How many times do we observe a beta hat of 7? How many times do we observe a beta hat of 5? How many times do we observe a beta hat of 16 when we calculate all these beta hats from all these different possible samples? So that's the mind game, the thought experiment that we engage in. That sampling distribution of beta hat is what we're interested in. We want to know whether this beta hat that we've calculated using this sample, is it part of a distribution that's very dispersed or broad with high variance so that any beta hat could have been estimated from data, or is it drawn from a distribution of beta hats that's very tightly centered? So the ideal thing we would want, of course, is that our distribution of beta hats is tightly centered, and sure, there's some outliers, but most of them are around in this range with high frequency and are very close to some true value of beta. So this would be the beta that's the true value. We'd like a beta hat that's very tightly distributed around that true beta or population beta. And we'd also like to know whether the distribution is a normal distribution, because that will enable us to easily make inferences about the probability of any given beta hat that we draw being more or less close to what we think of as our hypothesis of the true beta. So not surprisingly, we are going to show that beta hat, with a few assumptions, is going to be normally distributed. So for that, we're going to start with our definition of the regression coefficient beta hat, and we're going to go to page 141 of Stock and Watson, do a little bit of algebraic manipulation, and end up with this expression where beta hat consists of two terms: beta, the population beta, the true beta for the population, and then this term that has a numerator that's the sum of xi minus x bar times ui, which is ui is the residual or the error term. And then in the denominator we have the variance of x, xi minus x bar squared. So the distribution of beta hat, that's what we're interested in, is going to be the distribution of this numerator. It's going to be close to this distribution of this numerator. And that's because beta 1 is just a number, so it's not a random variable, doesn't have a distribution. And the denominator here is the variance of x. It's also just a number. It's the variance of the explanatory variable x. So the distribution of beta hat is going to depend on what the distribution of this term is, the sum of xi minus x bar ui. So notice for that term that as n goes to infinity, x bar approximates the mean of x, the population of mean of x, and that's just coming from our the sample average as n gets large is going to approximate the population average. So we can replace that x bar with mu of x, and then we have in the numerator 1 over n times the sum of xi minus ux, and all of that multiplied by ui, the error term. And let's call that that expression that's inside the summation sign, it's called that VI. So it's just a random variable. VI is a random variable, so different sample, different draws from the sample will give us different VI, and we're taking the sum of all those VIs and dividing by n, so that's just the average of the VIs for the sample, so that's just V bar. So the numerator is some average. We can think of it as some average from the sample, some number V bar. Remember that the central limit theorem tells us that if we have a random variable z that's independent and identically distributed, and let's think of this z as being like this vi, right? So vi is independent and identically distributed because the ui's are independent and identically distributed. If we have a random variable z that's independent and identically distributed and has expectation of z equal to some number and variance of z equal to some number, and the variance is finite, well, this vi has some expected value that's some number, and it has some variance that's also going to be a finite number. The central limit theorem tells us then if we have a random variable that satisfies those minor requirements, then as n goes to infinity, the distribution of the average of that random variable, in our definition here it's z bar, in our case it's v bar, the distribution of that average, when we normalize it, so we subtract the mean and divide by its standard deviation, that distribution is a normal distribution with mean 0 and variance 1, the standard normal distribution. Central limit theorem tells us that the mean of a average variable, the mean of a random variable, the mean of draws from a random variable will be a random variable itself that is normally distributed. So now we know by the central limit theorem, so we appeal to the central limit theorem. The central limit theorem tells us then that this V bar, which has mean and finite variance, and so it's normally distributed. And in particular, if we normalize it, so V bar minus UV over sigma V follows the standard normal distribution. So it follows the standard normal distribution. So that means that V bar itself will be distributed normally with mean 0 and variance sigma V, which is the variance of the underlying VI, sigma V divided by n. So that'll be its distribution. Now if we go back to our expression, we had the numerator, which we've just been looking at, and then we had the denominator, which was just the variance of x. The variance of x is just a number. So we come back to beta hat is equal to beta plus v bar. And remember that I've substituted in the population mean of mu x here, so that's why it's approximate as n gets large, and the variance of divided by the variance of x. So this is normally distributed. This whole expression then is normally distributed with mean beta, because the mean of expected value of v bar is just equal to 0, if you recall, because we have the expected values of the u's are equal to 0. So now we go to the variance of beta hat. The variance of beta hat then is equal to the variance of beta plus the variance of the second term. The variance of beta, since that's just numbers, is 0, doesn't vary. So the variance of beta hat is equal to the variance of this term. Well, remember, variance of x is just some number, so by the rules of taking variance, we bring that out as a square, so we have 1 over the variance of x squared times the variance of v bar. So that's 1 over the variance of x squared times, now we bring in what we know to be the variance of v bar is sigma v squared divided by n. Then we bring the n over to multiply the variance of x, and we end up with this expression where I've substituted back in for what the variance of v is. I've substituted that back in here. So we get this term. Beta hat is normally distributed with mean beta, the underlying true population mean, and variance, that's this number. This again looks like a complicated number, and we're going to worry in the next slide about how to estimate, the next video about how to estimate this. But remember, we need this, we need to estimate this, and we need to have this expression that it's normally distributed because we need to test hypotheses about beta hat. So we need to construct a t-statistic, beta hat minus HO divided by the standard error of beta hat. And what we've done here is show basically that that's going to be distributed normally with mean 0 and variance 1. So what we've done in this video is show, is sort of sketch how the variable beta hat is normally distributed, and we've characterized what the variance is of that so that we'll be able to estimate the variance of this beta hat estimator, and then we'll be able to do hypothesis tests.